Hi, everybody. Today I'll be talking about our work on detecting SSH imposters. This was done at UC Berkeley with Aashish from LBNL and Vern and David, my advisors at Berkeley. So we all know SSH. It's a useful protocol to remotely access servers and use interactive shells. It relies on user credentials to log in. So that's great. However, if these credentials are stolen, any other user can log in instead, and specifically with the same privileges as the main user. And the server can't tell the difference. From the server side, it's the right credential. MFA makes this a little bit harder, multi-factor authentication, because in this case, you actually need to have multiple identities, multiple credentials to log in. But once MFA devices are stolen, if you have a stolen phone or a stolen TOTP app, we're back to square one. Somebody can take all your factors, authenticate, and the server can't know. So the question here is, how do we detect SSH imposters? And our solution is to rely on user behavior. Specifically, we look at keystroke authentication. Prior work has shown that keystroke authentication is a well-researched form of authentication that shows that typing patterns are unique. And for instance, here, we can tell apart a legitimate user from an adversary because of the way they type. It's transparent for users and also very difficult to usurp. However, if we look at existing work, it uses keys, so the specific keys that are being pressed, key press durations, so how long you stay on each key, and also inter-key press durations. And the issue is that in SSH, we really only, everything's encrypted, so we don't have that information. This would require using keyloggers, which one, invade user privacy, and also are a big deployment hurdle. We can't have keyloggers on every single server. It's just impractical. So how can we do this? Well, let's look at SSH, and let's look at how keystrokes work in SSH. In SSH, let's say I want to type in the command ls. Every single keystroke is going to be sent as an individual packet to the server. It's going to be echoed back and then displayed on my terminal. Same thing for the S here. And so this means that each keystroke is its own packet and is echoed, meaning one, I can identify a keystroke because there's this echo, this sort of ping-pong behavior, and two, I can recover timing by looking at the timing of the client's packets. So that's great, but we still don't have the keys. We still don't know what the user typed, and we still don't know how long they pressed on each key. We just have a time series. And is that enough to figure out who's using the session? Well, that's our surprising result, and that's what we're happy to share, is that we found that yes, using only the keystrokes, timings, is enough to scalably and accurately authenticate people. So to be able to show this, we leverage a real network with over 600,000 unique SSH sessions over 5 years, and developed our own deep learning tools to show that we can authenticate user as little as 10 seconds from the beginning of the session amongst hundreds of unique users with under 4 minutes of traffic per user for training data, and specifically in real network environments with congestion. So this can be applied anywhere. So let's look at our system and how it works. So let's say here there's a client and a server, and we have this traffic capture. First, the client's going to authenticate. From this, we extract an ID from the system logs. We know who authenticated. Now, for each new packet that the server gets, we record the arrival time. And specifically, we record the inter-arrival time, this T1, and put it in our feature vector. And we do this for the next packet as well, T2, and et cetera, for all the next packets that are going to get here. And once we build this feature vector, at any point after a certain number of packets, we can pass it to our deep learning model that's based on a transformer and see if we have a match between the user ID here and the sequence. If we do, that's great. We confirm that this ID corresponds to this keystroke dynamic, and so the person is well authenticated. If we don't, we know that there's a mismatch, meaning the user is not who they pretend to be. In this case, there's several measures that we can take, depending on the security sensitivity of the site. It can be as simple as just logging the anomaly. But for more security-sensitive sites, such as government sites and stuff like that, we might want to actually terminate the connection to prevent future damage. And for brevity, I'm not going to go into all the details about the deep learning, but there's one technique that I want to highlight because I think it's interesting in this context, and also allowed us to reduce the number of false positives by a factor of 2. And this is something we call the partition layer. So our observation is that if we look at the values of these inter-arrival times, the times between packets arriving, the specific values aren't as important as the order of magnitude. For instance, knowing that there was 2 milliseconds or 2.1 milliseconds between two keys isn't as important as knowing that there was 2 milliseconds or 10 milliseconds. And to formalize this, we can see that we want to take all these continuous values and actually discretize them into bins. So for instance, we care if a packet's under 3 milliseconds, between 3 and 7, or above 7. This is just an example for the slide. And we can further look at this as a sort of membership function. We have these 3 bins, the blue bin A, the red bin B, and the green bin C. And each bin assigns 1 if it's in its range and 0 anywhere else. So for instance, interval time of 2 milliseconds, which falls here, would have this vector. Bin A is 1 for this function and 0 for the other ones. Now this is great, but the thing is that figuring out the best ranges for our bins is a hard problem. And we want to be able to do this in an end-to-end manner with our deep learning, but we can't train on this since this is not differentiable. These functions are completely discontinuous here. So we deal with this by relaxing this to a Gaussian membership function. The idea now is that instead of having either 0 or 1, our membership in a bin is going to be a float number between 0 and 1 for each bin. And the advantage here is that these Gaussians are completely differentiable, so we can learn the best possible values in our deep learning framework. And we still have this sort of, we can still understand bin membership by looking at these values. For instance, 2 milliseconds here is going to have a value here of 0.7, then around 0 for the other ones. So by shifting to this sort of continuous soft membership, we're able to deal with this problem and actually have an end-to-end system that trains for the best possible bins. So now that I gave some insight on this specific technique that we thought was interesting and that could apply to other sequence problems, we're going to look at our specific problem and how we process our data to get to our results. And we were very lucky to have a unique data set. We worked with Lawrence Berkeley National Labs and got access to a network tap here between the lab and the world, so we could see any connections from any users in the world SSHing into LBL. Plus, we got access to their centralized system logs. And why this is cool, because with these 2 sources of information, we're able to build over 5 years of border traffic, over 600,000 interactive sessions with 4,000 users and almost 3,000 servers in a real network with zero congestion. So this is kind of a gold mine for being able to evaluate our system. And the process is the following. We train on 3 months of data. We take 3 months of SSH data. We train on that, and then we can actually use the system in the next month. More specifically, when we train, we select users with enough traffic. We can't train on users that have only 1 flow or no flows because we can't understand their patterns. And then we use negative sampling to simulate imposters. This means imposters in our system, since we don't have many examples of actual compromise, are just other users. The idea being we want to differentiate between a main user and other keystroke authentication dynamics. Finally, I mentioned it's 1 month. We can actually use this system for many months, but for optimal accuracy, it's good to retrain every month on the previous data just to maintain a good standard and limit false positives. Now onto the results. So what we did is that we took this huge data set and focused on 3 months in 2016 for our training and the next month for testing. We selected a threshold of 19 minutes of typing for an average user. So that's a certain number of keystrokes, but it turns out that for many users that type faster, it's considerably less typing. So that yielded almost 300 users. And on these 200 users, we're able to achieve a 2% false negative rate, meaning that we get 98% of imposters, while only getting about 17 false positives a day. Now, 17 might seem high, but when you think about it, this is a massive site with thousands of users, and here are 200 users that we can actually deploy the system on. This site has analysts always working there, so 17 a day is not terrible. It's still something to deal with, but it's manageable. And it turns out if we vary this threshold, we can actually develop more bigger or smaller models, ranging from a small model here that requires more training data, so a narrow typing per user, but is able to get down to 8 false positives a day with a very small 1% false negative rate. But we can also scale it up to a system that only using 4 minutes of typing is able to handle 400 users and only gets 29 false positives a day, so not that much more than the base system. So this shows how our system is designed to be scalable. It's not intrusive and also fast. We only need to look at about 10 or 15 seconds of traffic before we can make these predictions. Our models, even though we want to retrain every month, still are accurate for multiple months. And one interesting observation is that the low false negative rate stays true for years. Even if I take a model trained in 2016 and apply it now at the same network, it'll get many false positives, but I won't miss many imposters. And finally, it's also robust to congestion and can handle multi-device users, so users that have laptops and phones and connecting for all of them. We do have some downsides. There are some false positives, and we can't hide that, and those can have an operational impact, especially for sites that don't have the means to deal with it. So these need to be dealt with sometimes in an automatic manner. For instance, sending another factor to the user to ask them to authenticate in a stronger way. Another issue is user coverage. We can only do this for users that have enough SSH traffic. We saw that we can even do it for only 4 minutes of training traffic, but if a user only connects SSH once a year, it's going to be very difficult to build a profile for them. So in conclusion, we leverage keystroke dynamics to authenticate users, and this allows us to identify 98% of our injected imposters with a manageable load of false positives, and this is evaluated and proved on 5 years of real-world data at a real research site with hundreds of users. Thank you for your attention. Here's the link to the code in the paper if you're interested, and I'm open to take any questions.